Per ISTA, relay pumping is using 2 or more pumpers to move water over a long distance by operating them in series. It is essential for all ranks, battalion chiefs, captain, engineers, and firefighters to understand how to execute a large volume water supply over a long distance and requires coordination, training, and pre-planning. Situations that may dictate the need for relay operations to occur might include when there are large distances from the water source to the fire, large volume operations such as water towers, defensive fires, or fires where there is a significant threat to exposures, cul-de-sacs with no hydrants, mobile home and trailer parks, when there is elevation loss, even when the officer wants to get ahead of the curve by anticipating increased fire flow and taking actions to set up a relay. Let's explore some scenarios where relay operations can be implemented. This is an overhead view northwest of Brown Field. There is a simulated fire in one of the auto wrecking yards to the north of the airport along Pogo Row Road. The only hydrant is over half a mile away. This will require 4 engines to perform a relay operation, ideally as a series of reverse lays from the fire scene to the hydrant. The next location to look at is Las Blancas Court. This is an example of a cul-de-sac with no fire hydrant. With the fire at the end of the cul-de-sac, the only 2 hydrants are located on East Naples at the intersection of Hamul and Montserrat, which are to the east and west and respectively 1,000 feet away. With the intent of a fire flow of 1,000 GPMs in the circumstances as detailed in the cul-de-sac with no fire hydrant and or a distance greater than 900 feet, it is ideal for a 3-engine relay operation. The first arriving engine can perform a split lay from the beginning of the cul-de-sac to the fire scene and assume the attack pumper role. The next engine reverse lays from the connection point of the split lay to the hydrant and assumes the source pumper role, while the third engine assumes the relay pumper role and spots at the connection point. Last is an aerial view of Bison Mobile Home Park located off of 8th Street near Woodlawn Avenue, where there is a fire towards the furthest in unit. There are 3 hydrants in the vicinity, a hydrant to the east of the mobile home park on Woodlawn, a hydrant across 8th Street to the north, and a hydrant to the west on 8th Street. The water source selected is a hydrant to the west, which is 1,100 feet away. This avoids putting a supply line across 8th Street, which is a largely used thoroughfare, and avoids having the engine lay hose directly into oncoming traffic from the east. In this scenario, a 3-engine relay operation is implemented. It is worth reiterating that the 3 techniques of forward, reverse, and split lay can be used in different combinations to achieve the overall goal of getting the apparatus in the correct location to pump the water from the hydrant to the fire. Now we are looking at a location which presents a fire flow and elevation issue. This location is Songbird Lane near Otay Lakes Road, which has a driveway leading to the houses above where the fire is located. There is a hydrant at the beginning of the driveway and is 90 feet below the house and over 600 feet away. Of note, this will mean that the elevation of 90 feet will create a 45 psi of elevation loss because there is 0.5 psi needed to elevate 1 foot of water. While the 600-foot length of 4-inch supply hose flowing a desired fire flow rate of 1,000 GPMs will create 114 psi friction loss. This is because there is friction loss of 19 psi for every 100-foot section of 4-inch hose flowing 1,000 GPM. To maintain a minimum intake of 20 psi at the attack pumper, the total pressure loss from the water source to the attack pumper of 159 psi will need to be overcome by placing an engine at the hydrant to act as a source pumper. We're going to take a moment to review the water supply for the city of Chula Vista. As you can see on this map, Chula Vista is serviced by 3 water districts: the Sweetwater Authority to the west, the Otay Water District to the east, and Cal American to the south. This chart was produced by the Sweetwater Authority and shows recent data about one of the hydrants in their jurisdiction. Notice on the left side of the chart that there is a static reading of 49 psi. As we move our way down the curve and to the right, at 20 psi residual flow, this hydrant is capable of 1730 GPMs. This is just an example of a residential hydrant that can flow well above 1000 GPMs. In fact, a vast majority of hydrants can flow greater than 1000 GPMs, and that is exceptionally rare for a hydrant to have flows less than 1000 GPMs. These are a few examples of hydrants you may encounter, which have different combinations of 2.5 inch and 4 inch ports. Simply put, we need to do relay operations because of loss. That loss might be attributed to friction, elevation, or kinks. These losses in pressure are created by the turbulence of water moving against the interior walls of hose or pipe. This chart represents friction loss in different size hoses in relation to the GPMs flowing through the hose. The left of this chart has GPMs, while the top has the different size hoses in 100-foot lengths. The number where these two figures meet shows the friction loss in PSI for the given diameter of hose and given GPMs flowing through that hose. From this, we can see that a 100-foot section of 4 inch hose flowing 150 GPM is negligible. That's why it's blank. At 500 GPM, we are at 5 PSI. At 1000 GPMs, we are at 19 PSI for every 100-foot section of 4 inch hose. At 2000 GPM, it is really high at 77 PSI. With 2.5 inch hose at 150 GPM, we get 6 PSI for every 100-foot section. 500 GPMs, we get 55 PSI, and at 1000 GPMs, you'll notice that it is also blank. This is because it's not recommended to have those flows through that diameter hose. A forward lay is the method of laying hose from the water supply to the fire scene. In this scenario, the first engine requested the next engine to secure a water supply. A reverse lay is a method of laying hose from the fire scene to the water supply. In this scenario, the engine attacking the fire requests the next engine to secure a water supply. Observe the engine performing the reverse lay has the firefighter get off and hold the supply line while it is being deployed. A split lay is a combination of a forward lay and a reverse lay and requires 2 engines. The first arriving engine performs a forward lay from an identified location such as a corner of a street or a driveway entrance to the fire scene, while the second engine goes from the known location to the water supply. In this scenario, the first due engine identifies the driveway entrance as the connection point of the split lay. The second engine's firefighter gets off the rig and holds the supply line at the split lay connection point while the engine drives towards the fire hydrant. It is important to note the necessary 4-inch double male needed to join the two hoses together. Reviewing the positions of a relay operation, the source pumper will be located close to the hydrant and should be the pumper with the largest capacity. The relay pumper receives water either from the source pumper or another relay pumper, raises the pressure, then supplies water to the next apparatus. During a relay operation, there may be one, multiple, or no relay pumpers. The use of a relay pumper, amongst other things, is guided by the distance of the relay operation. The attack pumper is located at the fire scene and, depending on the distance of the relay, receives water either directly from the source pumper or a relay pumper and is responsible for supplying the attack lines. Officers need to make determinations of resources based on the current and potential volume needs of the incident, or the distance from the water supply. We can use two different formulas to help us calculate the fire flow need. The first is the NFA formula, which takes the length of a building times the width, divided by 3, and multiplied by the percent involved. While the Iowa formula takes the length of the building times the width times the height divided by 100 to get the fire flow needed. There are different tools officers can use to identify hydrants and potential data, such as MDCs, tablet command, the Metro Zone grid book, blue reflectors on streets, or by pre-planning where you may discover private hydrants. Other considerations can be seen in SOG 2.1 primary staging, which states the first arriving engine company will respond directly to the scene and initiate appropriate operations. With that being said, appropriate operations in limited access situations such as mobile home and trailer parks, cul-de-sacs with no hydrants, could include actions such as a split lay. Later arriving engine companies should stage at a hydrant and not pass their water source. Engineers need to consider many things during these operations. A few of these considerations being, the attack pumper should be the only engine with the pressure governor in pressure mode, while the source and relay pumpers will be in throttle or RPM mode. Apparatus will need to maintain an intake pressure of 20 psi and determine their pump pressures. Attempt to minimize hose length used in the lay. Consider elevation loss or gain. Anticipate water supply needs. And consider the max working pressure of 4-inch hose being 250 psi. Firefighters also have considerations to be mindful of. These include understanding how the components of different lays come together, such as a forward, reverse, and split lay, and knowing the difference between performing a lay wet or dry, and knowing when the need for critical fittings, such as a 4-inch double male, are needed, like in a reverse or split lay. Formulas can help us determine how many pumpers are needed in a relay. One such formula is P equals R divided by D plus 1. Before we break down the formula, one given that must be understood is that 900 feet has been determined to be the max distance between CVFD engines. This also keeps 2 sections of 4-inch hose in our bed if the need arises to replace a section of failed hose. Going back to the equation, P is the total number of pumpers needed, R is the relay distance, D equals 900 feet, which is the Chula Vista max distance, plus 1. A quick reference chart has been adapted for the Chula Vista's needs and is based on a desired fire flow of 1,000 GPMs. This chart breaks down the distances of the lay and gives you the number of pumpers needed and the roles these pumpers will assume. Take note that at a distance of 1,800 feet to 2,700 feet, all pumpers on a first alarm will be exhausted. Going even further, at 4,500 feet to 5,400 feet, which is approximately a mile, at least 7 engines will be needed. Another formula to keep in mind is the formula for total pressure loss, which is the following. Total pressure loss is equal to total friction loss plus or minus elevation loss, elevation gain, plus 20 psi. Total friction loss can be derived from the fire flow requirements, total length of hose in the layout, and hose diameter. Elevation calculations are based on plus or minus 0.5 psi per foot of water up or down. The plus 20 psi comes from including the minimum intake pressure of the receiving engine that is being pumped to.
Metro, Engine 1's at scene of a large recycling yard with heavy fire showing. Engine 1 will be preparing for master stream operations, requesting second and engine to perform a dry reverse lay from Engine 1 towards the hydrant for a relay operation. Engine 1 is establishing PSAOIC and the defensive strategy. Metro, start a second alarm.
SAOIC, engine 2 at scene, and copies reverse lay from engine 1 towards hydrant located at the corner of Rancho Del Rey Parkway and Paseo Ranchero, requesting an additional engine to complete the operation.
Copy, Engine 2. I'm going to be assigning Engine 3 to assist you with the relay operation.
SAOIC, Engine 3 is at scene. Copy, assist with the relay operations and coordinate with Engine 2.
Engine 3 from IC. Yeah, that's affirmative. Assist Engine 2 with relay operation.
Engine 2 from Engine 3 on TAC.
Engine 3, perform a dry reverse lay from engine 2 to the hydrant located at Rancho Del Rey Parkway and Paseo Ranchero. Have your engineer assume the source pumper role.
Copy, reverse lay to the hydrant and Engine 3 engineer assume source pumper role.
I see engine 2 on TAC.
Go ahead, Engine 2.
Relay operations are in progress with engineers from engine 3 as a source pumper, engine 2 as a relay pump, and engine 1 as the attack pump.
IC copies. Relay operation set up. Engine 1's attack, Engine 2 is relay, and Engine 3 is the source pumper.
As the relay operation unfolds, we will now focus on the individual roles of moving the water from the hydrant to the fire. Pay extra attention on how the engineer increases the 2.5-inch port on the hydrant to 4 inches, which will allow the use of a second 4-inch intake line. This decreases friction loss of water coming into the pump and maximizes available flow of water from the hydrant. He now removes all kinks, confirms the pump is in throttle RPM mode, and checks the intake gauge readings to see the static pressure readings, and checks the master discharge gauge to verify the individual discharge gauges. Lastly, begins throttling up to the starting pressure of 120 psi. Transitioning to the relay pumper, the engineer also confirms the pump is in throttle RPM mode, then opens the intake. Verifies the intake pressure, opens his discharge while he continuously monitors the intake. Then throttles up to the standard starting pressure. Now we move to the attack pumper, where the engineer has already confirmed that they are in pressure mode and opened the intake valve. The engineer now begins pumping the desired discharge. The engineer is trying to achieve the rated pressure while continuously monitoring the intake gauge. If the minimum intake of 20 psi is reached, communications must occur to see if there is more water that can be moved to the attack pumper. One position that needs to be discussed is a water supply officer. It is recommended that this position be occupied by a fire captain. This position needs to maintain a span of control and consider how communications will occur and possibly ask for an additional TAC channel. Using similar principles, let's discuss water tower operations. Best practice dictates having an attack pumper spot 50 feet away from the ladder truck, but no more than 100 feet away. This is due to a few reasons. The first is a working pressure of 4-inch hose being 250 psi. A ladder truck at full extension and elevation needs about 220 psi at the base to achieve 1000 GPM flow. If we calculate the friction loss in 4-inch hose at 1000 GPM flow, which is 19 psi for every 100 feet, we can see that at 100 feet away, we will be pumping close to the working pressure of the hose. For this reason, it is recommended to have a pumper spot within 50 feet of the truck so that the apparatus are not maxing out the working pressure of the hose. This animation shows the optimal representation of this principle. One limitation to keep in mind is the limitation of OES 420. It is rated at 1250 GPM at 150 psi and only carries 3-inch supply hose. The order that a relay pumping operation will start and stop can change from department to department and is variable based on factors such as intake relief valve pressures, intake relief valve type, minimum intake pressure limits, and preference. Let's go through our standard method for starting a pumping operation. The source pumper will confirm they are in throttle RPM mode, then pump to the relay pumper with a standard starting pressure of 120 psi. From there, the relay pumper, whom is in throttle RPM mode, will pump to the attack pumper with a starting pressure of 120 psi. Now, the attack pumper will begin pumping to their desired discharge pressure and flow. It is key that the attack pumper maintains a minimum intake of 20 psi. Once the intake begins to go below 20 psi, the attack pumper will need to request an increase in pressure from the relay pumper, whom in turn will ask the source pumper to increase pressure so that they can maintain a 20 psi intake. With all that being said, the availability of flow in the relay operations is all based on the source pumper's intake readings, capacity, available flow from the hydrant, and the source pumper's engineer being able to maximize the volume of water at the designated water supply. Failures in hose line occur. Should this happen, pumpers can use the water in their tanks, but this is dependent on where the failure in the relay happens. Friction loss can be further reduced by having 2 4-inch lines. This can be 2 4-inch lines from the hydrant to the intakes, or 2 4-inch lines from the attack pumper to the 2 intakes of the tiller. A first arriving engine reporting directly to SEAM bringing 500 gallons without securing a water supply is effective in increasing the survivability of trapped occupants inside of a structure. A tactical consideration is an evidence-based concept for the fire service to consider implementing into department operations to enhance efficiency, effectiveness, and increase knowledge to accomplish their mission, to protect life, environment, and property. A first due engine initial action plan includes command and control, initiate victim rescue, a 360-degree walk-around assessment, consider transitional attack, and initiate interior fire attack.